guys, welcome back. I know that you're excited to start this lecture module because listen, no more nomenclature. Aren't you excited? Aren't you happy with that? Well, okay, I just lied. Yeah, there's going to be some nomenclature involved because I'm going to go back and review those nomenclature rules as we do these problems. But the focus of this lecture module now is going to include the reactions. Finally, in organic chemistry, we are going to be looking at the other half of these organic lecture topics, and that's going to be how these molecules react. Now, before I do that, I just really want to go through and bring back some of the old topics. What did we talk about last? Do you remember? I hope so. So we were talking about alkenes, and we were talking about how to name them and a little bit of the properties that were associated with those alkenes. So a lot of people will ask, hey, what's an alkene and why is this even important? Well, here's an alkene right here at the very bottom. Look at that. And this alkene is going to be ethene. Ethene, one of the simplest alkenes that we learned about and how to name in the last lecture module. Well, that ethene is also a plant growth hormone. Yeah, this is the stuff that makes your bananas go from green to yellow within a matter of a day after you bring them home. You can blame this molecule to do that. So this is a very common occurrence that is given off every single time that we purchase something like a banana, and it will continue to ripen and continue to grow and maybe go black and maybe go mushy, and then in our trash can down the drain it goes. All right, another alkene that we have is citronellol. All right, citronellol is an alkene. If you can look at it there's the double bond. But it's also an alcohol, which is why it ends in an OL, people. Look at there. It's all organic right there into the name, and now you know, and knowing's half the battle. All right, so there's OH, and that is the alcohol group that this is referring to. Of course, alcohol is actually going to get a higher priority over a double bond. So here is the OH group. That is the number one priority group. That is the most important, and that's where we start carbon number 1. And then as we go around, 1, 2, 3, 4, 5, 6, 7, 8, and then we can also talk about all of these substituents that come off of this main chain. It almost looks like it makes a circle, doesn't it? It does. I mean, it looks like if that OH group wasn't there, it looks like this would have maybe just continued on around and we could have got a cyclohexane ring out of it. Well, guess what, folks? We've got a version of that too, and that's called limonene. So the next time you buy a lemon and the next time you smell that lemon or grate that lemon and you get that citrusy, oily substance on your fingers or in your mouth, you can thank limonene for that. That is a circle. It's a cyclic structure. And we have a double bond that's here, and we have a double bond that's there. We also have some substituents that hang off of that we would name. However, we're not looking at IUPAC names here. This is a common name that is associated to that particular molecule. And something else that's also related in the alkene world that's very similar to what you're seeing on the screen right now for limonene is eucalyptus. So eucalyptus, if you look at the differences here, it looks like here's a difference, right? So that double bond is there on the isopropyl group in a way. So it's not there in the eucalyptus. However, that double bond that was here was moved, and it's moved through the molecule, and it looks like it goes up here to the top, right there. Limonene did not have it there. Limonene just had a straight single bond all the way to a methyl group. All right, so there's a couple of real-life alkenes that we can now associate with to tell you, listen, what you're learning in here is not waste. Now you know what's in a banana, and now you know what's in a lemon. And many of you would say, well, isn't that waste as well? Well, kind of, but at least it makes me feel better. All right, so now we're going to focus on the reactions of alkenes. We've talked about how to name them. We've talked about physical properties of them. Now we need to go through and we need to discuss how reactions are going to begin to happen in organic. And this is half of the lecture theory that people really do dread. You know, they do not look forward to reaction lectures. I don't know why, but they hate them. And here's my trick. I always look at these organics as relationships. And these relationships are typically a couple that goes into a bar, and on a Friday or Saturday night, they're probably going to get in trouble. And we're going to talk about how they get in trouble. And we're going to talk about how this relationship changes at the end of the night. And as long as I can maybe put it in that type of perspective, I think that you will have a better understanding, and I think that you will enjoy learning about the reactions a little bit more than if this was just a cut and dry lecture hall of 100 or 200 people. Nobody wants that. Give me a break. I don't even want to do that myself, right? I mean, I've been doing this for years. I'm going to kind of push the boundary a little bit and push some people's buttons just so I can get your attention and just so that you can enjoy organic chemistry maybe a little bit more. All right? So we are stepping into the world of our organic chemical bar. That's where we are. All right? Okay, so before we talk about any reactions, there's a couple of things that I want to discuss with you. Some of this stuff was addressed in the last lecture video at the very end of the nomenclature of alkenes. So during that time, we discussed this concept of a nucleophile and an electrophile. Okay, well, hopefully you can define those, because those are going to be coming back in this lecture in full force. Yeah, we're going to have to talk about these all the time. Nucleophiles and electrophiles. What's going to be reacting? You can't have one without the other. You got to have both in order for an organic reaction to form some product. And we're going to have to be able to comfortably discuss the difference between a nucleophile and electrophile. Okay, so a nucleophile and electrophile, we said, I know this is horrible, but it's like a pedophile. It likes something. It likes little things, right? And what kind of little things can it like? Well, electrophiles are electron loving. And nucleophiles love to be neutral. Okay, that's the way that I look at this. So nucleophiles are typically negative. They have some type of negative charge. They have some type of electron pair. Something is carrying a negative charge and they want to get rid of it. Okay, it's like your bank account. You don't want your bank account negative, do you? I hope not. All right, well, if your bank account is negative, one of the first things that you want to do is get rid of the negative. You want to be on the positive side, right? So nucleophiles behave the same way. Electrophiles are electron loving. That means these are like the millionaires and billionaires, and they have tons of money, and they love to spend that money, and they love to just fish it out left and right, left and right. They don't really think about it at all. Electrophiles want to be more negative. They want those electrons, and that's why we call them electrophile. So typically, these are the positive side of the house. So that makes sense. Positive pieces attract negative pieces, and those negative pieces could be electrons, and that's why we call them electrophiles by definition. Okay, so nucleophile, electrophile come together and they form a relationship, and a reaction happens and we get products. Now, we've already discussed really one type of reaction. That was in the end of the last lecture module. Okay? That particular type of reaction has a classification, and that classification is called an ear. That's what I call it, at least. So there's tons of different ear reactions that we're going to be learning about, and ear represents E for electron, the A for addition, and the R for reaction. If you don't want to use electron, you could also use the word electrophilic. It both means the same thing. All right. So we're looking at electrons. Electrons are the driving force here. And in particular, we're going to be looking at the relationship between the electrophile and a nucleophile that comes in and makes this nice little marriage that will give us some products in the very end. Typically, these ear reactions are two-step processes. 2 steps. Normally what happens, number one, is a carbocation forms first. Okay, so we've talked about carbocations, haven't we? These are carbons that are positive. Okay, at least I hope that you can define it. Because if you've defined it, then you've paid attention. Carbo means carbon, cation means positive. So a positive charged carbon at least has to be formed. Okay, so a carbocation forms first, and then this, of course, creates the positive piece, and this positive piece is then going to attract the nucleophile that we have in the reaction, or that we form in the reaction. But that positive will end up attracting a negative, and that positive will not stay around. Okay, I'm going to say that again. When the carbocation forms, that's great. It's fine. Yeah, so what? It's not going to stay forever. It actually forms, and within milliseconds, it will begin to have problems. It will go through a period where it will self-judge itself, and it will say, you're not good enough. You're not good enough, and you don't need to be here. And I need somebody in a relationship. Or I'm really, really lonely. That's what the carbocation says. Now do you see where I'm going with the bar chemistry? So because it feels extremely lonely and by itself, it wants a partner so bad it can't stand it. And it will go out the night of the breakup and try to find somebody else. That's how crazy the carbocation is. So that carbocation will form a positive charge, and it will immediately go out and try to form a new bond with a nucleophile, something that will carry a negative with it. So that's going to be the common theme throughout all of these reactions that we're going to get ready to discuss. They are all electrophilic addition reactions, and in my eyes, they're electron-driven. It's all about the negative pieces. And when these reactions begin to happen, 2 things will always go on. Number 1, you will always get a carbocation in these reactions. And number 2, when that carbocation forms, it will not stay around, and a nucleophile will come into the picture and take the spot of that carbocation. Now, here's the thing. What we're getting ready to learn, I keep talking about these products, right? Well, we're starting with alkenes every time. In all of these examples, these are alkene reactions. That was the title of the lecture, alkene reactions. We're going to start with alkenes almost every single time. That's why we titled it that. Well, when those alkenes begin to react, they can form a couple of different products. Okay, well, first, I could take an alkene and I could make an alkane. You know what an alkane is. We've talked about it so much, you probably dream about alkanes at this point. Well, that's not the only thing that we can do, though. Those are one types of products that we can get. The other types of products, though, it's all of the functional groups that we've talked about so far. So we can talk about making alkyl halides. You know, these are the things with the chlorines and the bromines, the iodines, all of those on it. We learn how to name them. Now we're going to learn how to make them. Alcohols. Again, we learned how to name these. We know what those are. Alcohols are the OH groups, right? So we learned a little bit of the basics of how to name an alcohol. IUPAC and common name. But now we're going to learn how to make some of those alcohols through these alkene reactions that we're going to discuss. Okay, well, ethers. Ethers we talked about as well. These were RORs, oxygens sandwiched in between 2 carbons. Imagine that bar description there. You'll get it. So these ethers will come around, and these ethers are going to say, hey, listen, I'm sandwiched in between two carbons. So we learned how to name those, IUPAC and common, but now we're going to learn how to make them. And we can make ethers through the route of alkenes. And folks, this is just the beginning. And there's so many different ways to make alcohols and to make ethers and to make alkyl halides, but we're only going to limit our discussion with alkene reactions, and that is it. No more. Just alkene reactions, and that's all. Okay. So now that I'm giving you a path, I want to go back and I want to bring in kind of the reaction that we started or that we ended up with in the last lecture module. We had an alkene, carbon double bond carbon. I'm just going to put 2 prongs here. Doesn't matter what's there. I don't care. You shouldn't care either. We're going to focus on the double bond, and that's it for now. Double bond. And we reacted it with HBr. All right, so here's the Lewis dot symbol for HBr. Look at that. Lecture 1 material all over again. Lewis dot symbols. So in this reaction scheme, we discussed a couple of things. Number 1, we said, hey, HBr, this guy's polar. Lecture 1 material. And I know it's polar because I see electron unequally shared among all the atoms in the molecule. Bromine's hoarding them all. Talk about stingy and greedy. Bromine's the one that you don't want to get in the relationship with. It's going to take everything that you own plus more. Nobody wants that type of thing, right? Well, bromine is an electron sucker. And that electron sucker is called electronegativity. And bromine has a very high electronegativity value. So those very high electronegativity values tend to give you a partial negative distribution in a polar compound. Look at there. Look how smart we sound when we start using our words. Okay, well, if there's an unequal sharing here, that also means that a partial positive begins to happen on the hydrogen. So, bing, there you go. There's the polar molecule that we are bringing into the world of the alkene. All right, now over here on the alkene side, this alkene side has a double bond, and that double bond, there is a large source of electrons that are there. This large source of electrons carries with it a negative charge. Right? There's more electrons in that core. It's more dense in that alkene double bond. Those carbons are sp2s. They're a little bit more open as far as their geometry goes. Look at that. I'm now bringing in lecture 2 and lecture 3 material. Gosh, we're good. So a reaction happens between here. And this reaction begins at the negative. There we go. And I draw it to the positive piece. That's the way we said we draw mechanisms every single time. It's not going to change here. So I start at the negative and I point it to the positive piece. There we go. There's the first step of the mechanism. I've now grabbed that hydrogen and it's going to be pulled off. This double bond is going to go into the bar and it's going to say, hey, hydrogen, I know that you're really not in a good place right now. And I know that bromine's high maintenance and you just don't want to deal with it anymore. So why don't you just kind of come with us and we'll just kind of sneak you out of this bar and you can leave just bromine out there on his own or her own. Well, hydrogen says, okay. And hydrogen goes off. Well, these electrons, they have to go somewhere, right? So where do these electrons go? Bromine sucks them all up. It's electronegative. That's what it does. So I need to draw that arrow and I need to show that electron movement of where those begin to go. So when that happens, remember I told you ears, 2 things happen, right? And the first thing that happens is a carbocation is formed. All right, well, this double bond is now destroyed because the carbons bit off more than what they could chew. Okay, so here's the two prongs that were on that one. Here's maybe the two prongs that were on the right-hand one, and we had a double bond that was there in between them. Well, that double bond, we now have a problem. It coaxed hydrogen into leaving bromine and coming onto that molecule. So this cannot stay anymore because carbon needs to make room, and that room is going to come from the breaking of the double bond, and now these two carbons open up a site of attachment. Hydrogen is going to go on one of them. All right, so I'm going to draw this hydrogen in blue, and hydrogen is going to go on one of those structures. These other ones, it could have just been hydrogen. I don't care what they were. It could have been anything, right? We left them blank. I don't care. But that new hydrogen came onto the carbon. One of them in the double bond, it came onto one. I just drew it to the left. Well, the one on the right-hand side feels left out now. Oh, boo-hoo-hoo. You know, you broke the double bond. I thought we had something good going on, and now you just broke it. You found a new buddy, and this hydrogen came in and just took up the space that I was actually giving you. And when that begins to happen, this carbon has nothing to bond to in the beginning. And because of that, it is shortchanged a bond. And that gives it a formal charge of plus. +1, formal charge, lecture 1 material. Look at that. So we need to give carbon a little bit a boost, I guess, in the self-esteem. We need to tell carbon, listen, it's going to be okay. You're going to find somebody. You're going to find somebody. It might take some time, but there's somebody out there for you. So this carbon is now a carbocation. And that first step has now just been satisfied with the ear reactions. Well, good news. Good news, because that bromine that coaxed hydrogen to get away from, that's still swimming around in the bar. And that carbon that's formed a carbocation says, you know what? I really like the way that bromine looked. And ever since that night that I ran across the H and the Br, I've not been able to stop thinking about that bromine. And I'm going into this bar, and bromine's there, and bromines by themselves, and I think I'm going to make a move. Well, that's perfectly okay with bromine, because look, bromine is negative. There's the nucleophile piece. And this carbon is positive. There's my carbocation piece. And curvy arrow says you start at the negative, and you draw it to the positive piece. So I draw it to the carbon. Well, when that happens, we finally have a molecule that's now happy. And that molecule used to be a double bond, but now that double bond has been broken. And on one carbon, I get a hydrogen from the HBr. And on the other carbon, I get a Br from the HBr. Folks, this very first step, this is the slowest step, as you can imagine. You know, here you've got a carbon that really has a nice bond between each other. And you have this HBr that is in a bond. It's unequally shared, but it's been there for maybe quite some time. And they are very hesitant in leaving what they know. So this is going to be a very slow step. It's going to take some time. As you can imagine, if you had a friend that was in a bad relationship, it's going to take you a little bit of persuasion in order for them to see the light. However, once this happens, folks, it is all game at that point. All kinds of things happen in all of these reactions. And after that point, when these carbocations form, they are going to go very fast. So if you start talking about rate limiting steps, you know, which step is going to be a rate limiting step? Well, it's going to be the very first one in most of these ear reactions. And the reason is because you have to rely on these bonds to break. They're very comfortable right now, but they're going to have to break, and they're going to have to form new bonds. And that typically is the slowest step of every one of these reactions. But once the carbocations are formed, once those positively charged carbons begin to surface, then after that point, these reactions happen very, very fast. They are not going to keep the carbocation very long at all. All right. So the products down here at the bottom, I'm not going to name this one. This is just an example, but I am going to go back and we're going to start reviewing the nomenclature of every one of these reactions as we form these products, if we can. Okay, so this gives us a very good chance to go back to that Lecture 3 and Lecture 4 material and just really review it as we learn new material in addition to that. So if you didn't get it the first round, then we talked about it in the second round. If you didn't get it in the second round, then guess what? We're going to talk about it again, and hopefully third time is going to be the charm. Okay, so there is the story with the electrophilic addition reactions. So this is where I'm going to stop the video. In the next video, we're going to pick up, we're going to do more examples of electrophilic addition reactions. I'm just going to kind of write them down onto a sheet of paper, get you familiar with them, and then we will start talking more details of these reactions as we move forward in this lecture module.